So this is a talk that was originally supposed to be given by Laura, but unfortunately she couldn't make it in person, so you're stuck with me. So I will talk about automating induction in saturation, and I will get to explaining what I mean by all these three words, but actually let me start by sort of a self-referential motivating example. So this is a screenshot of the Vampire codebase from some time ago. Currently, it encompasses around 250,000 lines of code. And it is in code bases like these and many others where bugs can pop up eventually, right? And we do our best to fix them. But the ideal that we're striving towards is to be able to have the process of finding bugs and hopefully also fixing them fully automated. So what we would like to do eventually is to have fully automated program analysis framework. And Vampire, actually, this is why the example is sort of self-referential, is a tool for automated reasoning that we would also like to use for program analysis. And to be able to reason about programs, we actually have to automate reasoning about all their components, right? And there are some constructions in programs that are sort of hard to reason about. So one of them are loops. And this isn't an actual excerpt from the Vampire codebase, it's rather a small toy example that helps me illustrate what I mean by reasoning about loops. So what this program does is that starting at some position P with an array A, we iteratively copy the value from position I to position I plus 1 until the end of the array. And given such a very simple loop, what we would like to do is prove that if the position P, in fact, is within the array, then after the code terminates, the loop finishes, all the values stored on positions between P and end of the array are the same and correspond to the value that is stored at position P. And we would like to do this in a fully automated fashion. So the process of proving this assertion will consist of two parts. First, we will generate inductive loop properties. This is part of our work that I won't be speaking about, but it can already be done automatically. And the invariant that we generate for such a loop is this one, saying that at this point in the loop, for all the positions between P and the current loop counter I, the consecutive two elements are the same. And once we generate such a property, then using this invariant and the assumption from the beginning and the negation of the loop condition, which will hold after the loop terminates, we would like to prove the assertion. And we can already see that for this, we might need some sort of reasoning with induction. Because the invariant that we have here is some property that's holding for two consecutive elements. And the thing that we want to prove here is sort of similar in form, but it is a property that holds for all the elements. Now the tricky part here is that since all of this comes from program analysis, we're taking also the types of all the constructions that we are reasoning about from the program. And in the program, I is an integer. So we would like to perform induction over integers, which isn't completely straightforward because integers aren't well-founded. So this is something that we have to tackle. And yeah, we would like to do all of this in the framework of saturation-based first-order theorem proving. And I will get around to explaining what saturation-based and first-order theorem proving mean in just a second. Yes?
Yeah, just a quick question. Do you just assume that everything terminates, or do you also have some smart way to figure that out?
In this example, we assume that everything terminates. But yes, I mean, there are... Yeah, it's a different challenge then to also prove termination. Okay, so this is the first thing that we would like to do, automate proving inductive properties over integers. The second construction that is also very common in programming is recursion. And so here we again have a very simple example. We're defining the data type of natural numbers. 0 is a natural number, successor of a natural number is also a natural number. And we recursively define the function of addition on natural numbers in the standard way. And given this, we would like to prove that addition is commutative. And this is, again, some inductive property, this time over natural numbers. And we would, again, like to prove it in our saturation-based first-order theorem proving framework. So overall, our goal in this work is to be able to fully automatically prove inductive properties over arbitrary data types, be it inductively defined data types or integers, and integrate this proving into the saturation-based first-order theorem proving framework. So in a way, our work is combining together all these aspects. So we're doing loop analysis, computer algebra, all that in the framework first-order theorem proving, and we call this automated reasoning about programs. And it is enabled by the support of all these sponsors and organizations. Okay, so automation of induction in saturation-based proof search is the moment where I promise to explain the individual words individually. So by automation here, I really mean full automation. The only thing that comes from the user is the input. That would be some logical formula. And then the user can also set up some parameters for the prover to run, and then runs it, and that's it. Like everything else is already done by the prover. The whole proof search, production of the proof, and so on. By induction, here I mean implementing the principle of mathematical, structural, and so on in induction within this fully automated framework. And finally, saturation-based proof search, I'll get around to that in the next slide. But I first want to mention that here I'll be working about the joint work that we did also with Marton Hajdu, Giles Ridger, and Andrei Voronko. So let's start actually with the saturation first-order theorem proving. And yes, so the first question that I want to answer here is what types of formulas are we, or what types of theorems can we prove with this saturation-based theorem proving? So we're working in this work with formulas in first-order logic, but note the asterisk here. The saturation-based framework nor superposition, they are not limited to only first-order logic. It is just what this work here in these slides are limited to. So we can also do higher order. I won't touch upon that. And these formulas can use quantifiers, and they can also use theories. Of course, the more quantifiers, the more theories we use in the formula, in general, the harder it becomes to reason about it. But we don't have any categorical limitations on how to use quantifiers or how to use theories. So the formulas that we are able to prove here are, for example, simple mathematical properties, such as that for if a group is idempotent, then it is also commutative. We can prove some simple formulas, for example, saying that if we sum up the integers between 1 and n, then we will obtain the same result as for the closed form formula for the sum. We can solve some not so pretty but practical problems originating from verification, for example, so stuff that maybe a human might want to actually look at, but we might want to have them proved. So to contrast this with what SMT solvers do, we had a really nice talk yesterday about quantification and quantifier elimination in SMT. So in this saturation-based theorem framework, we are better with quantifiers. We can reason with them in a more efficient way, but we are worse with theories in general. So this is a trade-off that you're making when you're choosing whether to use a saturation-based theorem prover or an SMT solver. And before I explain how we can prove all these formulas, I will actually show you that we can do it. So
did I miss it, or did you say what saturation-based means?
I will get around to that, but before I explain how it works, I will actually show you how it works. So the problem that we'll be proving is the group problem. So that for algebraic groups from idempotency commutativity follows. This is an encoding that we have for the problem. So it essentially consists of 5 formulas. The first one here says that we have left identity element. The second one here says that there's a left inverse for any element. Then the third formula here says that the operation is associative. Then we have the hypothesis saying that the group is of order 2 or idempotent. And then finally, the goal, the conjecture that we're trying to prove is saying that the operation is commutative.
This is the language that Vampire accepts?
Yes, Vampire accepts also other languages, but this is one of them. Yeah, so this is called TPTP language. So we can run Vampire on this problem, and we see that it very quickly, in well under 1 second, solves the problem and produces this proof. And I will actually want to go through the proof before explaining how it does it. So this is what we produce. This is like an extra pyramid. I removed some parts on the top and some parts on the bottom.
Is it non-deterministic?
It is mostly deterministic. In this simple case, it is deterministic. The reason why I say mostly deterministic is that, for example, we have a very efficient use of resources in Vampire, and sometimes if we are low on time or memory, we might change the proof search in some way. And that means that if you run on a different computer that has less memory, less time, then that might affect the proof. Okay, so this is the whole proof. It has something around 25 lines, I guess. And we can see, like it consists of multiple parts. We can see here that what we're actually doing is proof by refutation. So the proof finishes when we derive Folsom. And we can see at the beginning, the first couple of formulas are the input. And then formula number 6, that is the negated conjecture. So what we're doing in this saturation-based framework is that we take all our assumptions and negated conjecture, and we're trying to derive a contradiction from that. And the proof successfully concludes if we manage to do that. I will get around to that as well. So you mean that we're starting with 1 and so on and ending at 270, right? Yeah. Okay, I can answer your question now. So the reason for this is that at the beginning, when we're just trying to find the contradiction in our search space, we don't know which way exactly to go, right? So we're deriving many formulas, and hopefully one of them will eventually lead to the contradiction.
It was a scratch paper.
Yeah.
Oh, the other lines have been discarded.
Yes, essentially, like they have been derived, but they do not participate in this particular derivation of Folsom, so we don't display them here.
We just see one path in the tree that we generated.
Yes, we see the first path in the tree that led to Folsom, and then we stopped. So we.
Question.
Yeah.
It looks like you assumed 5 and 6, which are negations of each other, but that's not what you did, right?
Yes, that's not what we did. 5 is the conjecture that we obtained, and we don't. Yeah, like from. We immediately negated 5, and we only used 6 afterwards.
So 5 is not really an assumption to be used.
No, it's not really an assumption. It's yeah. This is just an artifact of how it is displayed in the proof.
So, do you have a sense of how big is the proof system, the sense of number of rules? Because there are many high-level rules there, right?
Yes. So there are, let me see, 5, 6, something like that, basic rules, and everything else can be essentially derived from them. But in practice, there will be many more, dozens at least, because we have rules that are efficient in particular cases and make the proof search much easier. Okay, so each step in the proof is deriving formula from 0 or more formulas that were derived before. So for example, here in step 21, we derive that using a rule called forward demodulation. It's not important what that exactly is, from formulas 15 and 10 here. There is a large part of the proof which is just pre-processing. This means that we are taking all our input and converting it into closed normal form and columnizing it. And this is the form with which we're then working. And then this part of the proof, that is the superposition calculus. So here we're applying rules of superposition calculus. I will also explain a bit more on that in the next slide. But essentially the point here is that we have a set of inference rules that we are using with the goal of deriving the Folsom. And yes, the final point here that we also have the unused formulas. So we have to be sort of careful in the way that we are conducting the proof search, so that we keep the property of some sort of fairness, that we eventually touch upon all the possible search paths in the search space. But at the same time, we want to keep this efficient. And you can see that already in such a short proof, we had to generate multiples of the formulas that actually were used in the proof in the end to find this one. So this was how a proof looks like. Now let's see how we were able to find that proof. So this is the saturation algorithm in its simplified form. If we want to prove a formula with respect to some set of assumptions or set of formulas S, we do it in the following way. We take the formula F, negate it, and add it to the set. From this point on, we'll call the set the saturation set or also the search space. And then iteratively, we do this process which we call saturating the set. So we choose some formula from the set, let's call it G, and apply the rules to derive consequences of this formula and possibly other formulas that are already in the set. Then we add these consequences back to the set and periodically check whether the set already contains false. So if it contains false, then it means that we managed to derive contradiction from the negated input and the assumptions, and hence the original input must be valid. On the other hand, if this loop here terminates without deriving contradiction, then in some cases we know that if the calculus is complete here, then we know that the original formula is not valid, because otherwise we would be able to derive contradiction. Now, in practice, this happens rarely for two reasons. One of them is that we might use incomplete calculus, so we sometimes sacrifice completeness in favor of being able to prove more stuff in practice. And then the second reason is that we might run out of resources, so time or memory, before we reach the conclusion and before this loop terminates. Yes?
What does it mean that the loop terminates in 2?
So, okay, yeah, the loop terminates when there are no more consequences that can be derived. Everything is already in the set.
Well, is that possible?
Yes, sure. Like if you have, let's say that the input formula is just PA, right? What can you derive from this?
PA and PA or something?
Yeah.
We don't have a rule for that, right? So in our
Sorry,
calculus,
can you say that again? You said it quickly. I didn't catch it.
so let's say that we have only this, or actually, let's say we only have this, right?
Those are not arbitrary logical consequences. They are carefully crafted consequences.
Okay, so
Yes.
that's my question.
Oh, okay, yeah,
Yes.
yeah. So actually, yeah, like it would be possible to also have this loop with any calculus that you wish, right? But in practice, since we want to be efficient, we have some selected inference rules that we're using to derive new consequences. So yeah, so I want to zoom in a bit on this saturation loop. So the first point I want to make here is that when we're choosing the formula on which we're applying these rules, in some sense we want to be fair, and we eventually want to go through all the formulas that we have. So we don't have this goal-oriented architecture in saturation. So this formula can be seen as really an arbitrary formula. So there is no guarantee, for example, that the first formula that we choose when we first run this loop will be the goal, the original f or the negated f. It can be any formula that is already in the set. Yes, a question.
Are we proving that f is consistent with respect to s, or that is a logical consequence?
That is a logical consequence.
Okay. Oh, okay, yeah. Cool.
Yeah. So in saturation, essentially, we don't have this goal architecture. So any formula here can be chosen, and hopefully every formula eventually will be chosen. Yes?
More questions. So you don't ever do reasoning by cases?
That would be, okay. I think that the easiest way to incorporate this with reasoning by cases would be then some splitting, and which is possible, and we do it with the avatar framework currently, and I don't want to get into details. Yeah, okay. And then the second point I wanted to make here is exactly about the calculus. So there are a lot of different possibilities of how to derive the consequences. And what we do in our theorem proof of empire is using the superposition calculus. And as I already mentioned in the previous slide, we're doing this over clauses. So superposition calculus can be seen as an extension of the resolution calculus to be able to also natively handle equality. And its name doesn't come from quantum computing, as I have actually heard suggested multiple times, but it comes from the superposition rule. And this is the simplified form of the superposition rule. It has two premises. It can be seen as rewriting by equality or conditional rewriting by equality. The first premise contains an equality between terms L and R, and then this C symbolizes the rest of the clause, so it can be either empty or contain one or multiple other literals. The second premise has a literal uppercase L containing the term lowercase l, and then rest of the clause D. And given such premises, we can combine these two to rewrite this lowercase l here to the lowercase r, and then combine the rest of the first premise with the rest of the second premise and derive this clause. Okay, so this is saturation and superposition in a nutshell. And now we can move over to how we integrate this with automating induction. So induction can be automated or implemented by reducing goals to subgoals. So let's say that we want to prove some goal that for all x, fx holds. And we can prove it by induction by reducing this to proving the base case of induction and then the inductive step case. However, this is not how saturation theorem proving works, because we don't have this goal-subgoal architecture. Because in this saturation loop, there is no clear notion of what would be a goal, and if we reduce it to a subgoal, then we just add it back to the search space, and again, we have a formula just like all the others. So our solution to this problem is to add induction as yet another rule in the calculus that can be used. And we do it in this way. So we introduce an induction rule. This particular is induction rule over term algebras. I will also get to induction over integers later, but let me start with this. So the rule has one premise. The premise contains a literal, not LA, and that is the literal that we'll be trying to refute by induction. So essentially, we'll be proving LA by induction. Now, given such a premise, the rule derives this complicated thing here. Let's first take a look at the content of the parentheses. The premise implying for all x, Lx can be any valid induction scheme. So, for example, the induction scheme that we see here, that is structural induction for natural numbers. Here I'm using the symbol 0 to denote the natural 0 and +1 as a shorthand for successor. So this would be the structural induction scheme for natural numbers that can be plugged in here into the parentheses. Now, the CNF here stands for causal normal form, and we are converting the whole induction scheme into causal normal form because our calculus works with clauses. So how does this play together with saturation? So again, in our saturation loop, in step 2.1, we would choose some formula. So let's say that we actually chose a formula that corresponds to, in its form, to the premise of the induction rule. And if we do that, then we can apply the induction rule and hence derive the consequence that is the causal normal form of some valid induction scheme. Now, the issue with this is that these clauses that we obtain by clausifying the induction scheme become just another ordinary clauses in the saturation set. And hence, we don't have any guarantee that they will be used to prove this LA as a subgoal in any near term. Question, yes?
Can you recall what exactly you call clause and clausify?
Oh, okay, yeah. So clause is a disjunction of literals. And by clausification, I mean the process of converting any formula to an equivalent clause or a set of clauses.
Again, what would be an example of that, a simple example of that?
So converting this to this. Or
This
maybe
is exercise 1 on my logical sets exam.
We don't learn any of that. Yeah.
yes. Okay. Also very important, we might end up with a set of clauses. So for example, if we had something like B and C here, then we would convert it into these two clauses. So yeah, so here we end up with some set of clauses that we add to the search space. But yes, there is not really any guarantee that we will use, no guarantee that these will be chosen next and that they will be immediately used to resolve away this not LA. So our solution to this is to tailor the saturation process to induction. And we're doing that by combining the induction step with a immediately following resolution step. So when we apply the induction rule, then we immediately take the causal normal form of the induction scheme here and immediately resolve it with the original premise of the induction rule. So we can see here that we have this literal not LA in the original premise, and we have the literal LX in all clauses coming from the induction. These are complementary literals, so we can match them and we can apply binary resolution on that. And we derive the clauses that correspond to the causal normal form of this thing. Yes?
I have a stupid question, but I don't know what you mean by resolve.
Oh yeah, okay. So that is the binary resolution rule, which I believe was already mentioned before. The way it works is that if we have, actually, let's do L. So we apply this rule. So essentially, if we have a literal and its negation in a different clause, then we know that at most, exactly one of this will be true. Hence, either C or D has to hold, and we derive this clause. Okay. So this means that if we do this, then the clause that was chosen originally, the premise is the same. But here in step 2.2, we apply both induction and then resolution. And then we add to the search space the result of both induction and resolution. So in this way, the LA is actually handled as a subgoal that we're trying to prove because we immediately get around to resolving that away. Let us take a look at the specific example that I've shown you at the very beginning. So we are trying to prove that addition is commutative for natural numbers. So here again, I'm using the plus symbol for brevity to represent the add function on natural numbers. So first step of our algorithm, we have to negate and scholemize our formula, and we obtain this literal here. So the sigmas are scholem functions corresponding to the variables x, y. Yes, columnization, that's also something that I think was mentioned yesterday. So essentially, what we can do, if we have a formula like this will be equisatisfiable with this for a fresh scholem constant S. Yes, yes.
So I guess the point is that if you have additional parameters, S will become a function of those parameters.
Yes.
That's why it's called a function.
Yeah. Fair. I should have used the term constant here. Sorry for the confusion. Yes. So okay. So the sigmas here are scholem constants that correspond to the variables x and y. Now we can get on with the saturation loop, and I have a question.
You also do scholemization for non-constant functions, right?
Yes. We can also, yeah. Okay, so now we can get on with our saturation loop. So far in our saturation set, we only have one formula. We choose that, and we choose to apply the induction rule on this. And we'll be applying it on term sigma 0. We might have as well applied it to sigma 1. The result would be symmetrical. We apply the induction schema that I've already shown you before. This is just a structural induction for natural numbers. And we instantiate it using this literal and obtain this instance. So this is the base case. The rest of the first line is the induction step. And if this holds, then we know that for any x plus sigma 1 is the same as sigma 1 plus x. Now, we take this induction schema and scholemize it and convert it to causal normal form. And we obtain the following two clauses. So here, this x is scholemized, and it becomes this sigma 2 here. So now we already have two sigmas in these formulas. So the first literal in both these clauses corresponds to the base case of the induction schema. The second literals correspond to the induction step case, and the lateral literals in both clauses correspond to the conclusion of induction. Now, we will resolve these clauses exactly as I mentioned before against the original negated goal, so the original formula that we're trying to prove. And by that, we remove these two literals, and we are left with these two clauses. And these two clauses are finally added to the search space. Now, these added clauses, first, are stronger than the induction axiom, because essentially they just correspond to the negation of the base case or negation of the induction step. So we already know that because we have this thing in the search space, that means that the conclusion of the induction axiom actually cannot hold, or we might be able to derive the contradiction from it. So in this sense, the clauses are stronger than the original induction axiom. And also, they are friendly to saturation theorem provers. And by this I mean two things. So first, they are quantifier free. which makes them easier to reason with. And second, they cannot be reused in many inferences. So now I'll first explain why, and then why this is good. So the literals that might have many consequences are namely the positive equalities. The only positive equality that we have here is this one, and that contains the symbol sigma 2, which is fresh and is actually only used in these two clauses and nowhere else in the search space. So this will be hard to match to something else in the search space and hence hard to derive something new from it. Now the question, why is this good that we don't have many consequences of these clauses? Well, the reason is that as you've seen already in the example where we had to derive 270 clauses to get to the FOSM, many inferences can be, in this sense, explosive and have way too many consequences that don't lead to the FOSM. So we want to keep our saturation set as small as possible while still not blocking any path that might lead to the contradiction. So it's good that we are not adding something that will have too many consequences that might not lead anywhere. So therefore, we can actually afford to apply this induction inference thousands of times during the proof search, and it will not affect the prover's performance too much in a bad way.
In effect, you are replacing induction with well-ordering principle. I mean,
yeah.
You're basically looking at the first counterexample.
Yeah. This also, I think, this ties to the question, how are we selecting the schema that we're using for induction? Because we're essentially like, that will lead to different literals here, and we can plug in different schemas and end up with different clauses. Okay, now, what do we do with these added clauses? So one thing is that they can be targeted by further applications of induction, and this is actually what we'll have to do if we eventually want to resolve them. So first, we could use splitting, as Clark asked about, but if we're not doing splitting, then we have to target these literals separately. But we can apply induction on that, and with an application of induction, we'll actually be able to resolve this part, and we'll be left with this thing. So we'll be essentially left with proving that the induction step case also holds. And, oops, what did I do? Nope.
You got to click on.
Okay. Cool.
So sigma 1 and sigma 2 are fixed, though, right?
Huh? Excuse me?
Where's the induction hypothesis?
Oh, so yeah. So this is essentially the induction hypothesis. This is saying that we know that the thing that we're trying to prove holds for sigma 1 and sigma 2. And from that, we want to refute that it doesn't hold for...
because we're trying to prove by contradiction.
Yeah.
Got it.
And but in general, this is actually like the clauses that we have there are very simple to, very similar to what we would obtain using the pen and paper mathematical induction proof. So exactly like asserting this, and we're trying to refute this from that.
And now, as a human, I'd want to develop a sort of sensible theory of algebra, like associativity.
Mm-hmm.
But you're just going to generate everything.
Yes.
And the very last line, you don't want the 90.
Yeah. So this is the thing, like sometimes in saturation-based theorem proving, we conflate the words refute and prove. So it might get confusing. Bear with me. Okay, but the key point here is that we are performing all these steps within the saturation framework, and all of this fully automatically. So to summarize, the approach to induction over term algebras, we are introducing a rule like this for some valid induction scheme, and we are tailoring the saturation process to induction by combining it with a resolution step. And this approach is generic in two ways. So the first one is that we can use this approach on any term algebra. We don't have to explicitly build. We have to build the induction scheme for any inductively defined type or term algebra that we have, but this can be done fully automatically. It doesn't require any human input. And second thing, any valid induction scheme can be used, and we can combine essentially any inductive type with any valid induction scheme. So we also have induction scheme based on some well-founded ordering and so on. And then we also extended this approach to induction with generalization, which will be based on the need that we have sometimes to prove stronger or generalized formulas instead of the original formulas. So let's say that we want to prove that addition of natural numbers is associative, but not for 3 different variables, but for the same variable repeated 3 times. If we just naively apply the approach from the previous slide, we won't be able to do it because we would be applying induction on all the occurrences of x, and in the end we would just end up adding more successors everywhere and won't be able to do much with it. So to prove this formula, we actually want to use an induction axiom for a generalization of that formula. And we're doing that in addition to using an axiom for the original formula. So what I mean by this is that we have this modified rule for induction with generalization, where, well, we have the same premise as before, but the scheme that we're using is actually a scheme for a stronger formula. So here we have the L prime, and L prime is a generalization of L. And again, the scheme that we're adding is a valid induction scheme, but it's an induction scheme for the generalized formula, not for the original one. And here the point is that we don't replace the goal that we're trying to prove, in a way, by the generalized form. And neither we are adding only the generalized version of the axiom to the search space, but we are leaving the prover a free hand in choosing how they apply the rules, and we have both rules, and we're using both rules. So in the end, we add induction axioms for both the original formula and the generalized formula to the search space. And then again, like, we'll see where the prover takes it from there. Yeah, this is a screenshot from the table of results of the generalization paper. We were slightly surprised that even provers that have quite good inductive reasoning at the time weren't able to solve many of the generalized or generalization-oriented benchmarks. So for example, the associativity benchmark here, the third one from the top. So CBC4 with some options was able to solve it, Superposition was able to solve it, Zeno was able to solve it, but other provers such as ACL2, for example, wasn't able to solve this, so they didn't have.
And vampire star is you?
Yes, so vampire without the star is vampire. Without the generalization, vampire star is vampire with generalization in this specific table. Yes?
Zip rewrite is what?
Zip rewrite is the proposition with some additional rewriting that they support. But again, this is, I think, for this one, we had to actually rewrite manually or automatically the input files so that they will include some rewrite rules for some of the function definitions.
But these rewrites, they are built in, or the user is adding them?
These rewrites are carried out by the proposition itself, but they need a different input file, if that makes sense.
L is the theory of fire strings or something?
Lists. Yeah.
So they can all find associativity if you state it correctly.
Yes.
If you just suggest consequences of it, then they start to struggle.
Yes, yes. So this is the
They
thing.
don't know which X to induct on.
Yeah. And this is also the, well, I mean, for saturation-based theorem provers, this is something that if we prove a formula, we don't really add it as a lemma or anything like that. If we prove it, then we essentially
It gets
refute
swallowed
it.
up into this clause system.
Yeah. So it is not simple to derive consequences of something that we're already proving.
You're thinking about it in a different way.
Yeah. Okay. To wrap up the part about thermal algebras, I want to quickly talk about the implementation questions. So the first one that we had to take into consideration is which induction schemas to use, because as I mentioned, the approach is generic and supports different induction schemas. And then the second, where to apply induction. So how to choose the clauses on which we apply induction, how to choose the literals in the clauses that we want to apply induction on, and which terms in those literals to apply it on. And our answer is essentially, we have a lot of options. We have some predefined options, but we can also leave it up to the user. So if the user knows what they're doing, they can set all this up to fit their particular problem. So we implemented different induction schemas. They can be turned on or off. And we also have multiple options on how to select the literals, how many nested inductions we allow to apply in the proof, how many generalizations we're allowed to do. And also we have an option for combining literals coming from multiple clauses into one induction scheme. And with that, I will actually switch over to doing saturation over integers. Oh, sorry, saturation induction over integers. But actually, one last thing I wanted to show you before going there is that we can, turning on the structural induction for vampire, we can prove the, actually, let me first start with So this is the problem that we'll be proving. This is the commutativity for natural numbers, this time written in a different syntax. This is the SNT-lib syntax you might recognize from some other talks this week. Essentially, this is the important part. We're trying to prove that plus is defined in this recursive way is really commutative. And we can do it with Empire by turning on the...
So it knows induction is valid.
Huh?
You didn't give it induction as an axiom, but it somehow knew it was valid.
I told it to use structural induction here.
Oh, I see. And so it figures out a structural induction principle for the data type.
Yes, yes. So the data type is defined here in the input file, and then we automatically build the structural induction scheme for that. And now the proof is somewhat longer than the one that we've seen for the group problem, but we can see that here we use the structural induction hypothesis, which is fully automatically built, and we see that it's actually the symmetrical one to the one that I had on the slide. So we kept the Skolem function 0, Skolem constant 0, sigma 0 here, and we replaced the other one by 0 in the base case, and then by something else in the step case. Yeah, so this is how it works. And now over to integers. I think I have like 6 minutes to cover that. That should be enough time. So the problem that I already mentioned at the beginning of the talk with integers, that obviously they are not well-founded, so how do we apply induction on that? And we take advantage of the very simple observation that any set of integers with a lower or an upper bound is well-founded, and we apply induction over intervals of integers, either finite or infinite, but with at least lower or at least upper bound. And we do this by defining these induction schemas with so-called symbolic bounds. So to take it word by word, by downward or upward, we just mean whether in the induction step we're doing +1 or -1. By symbolic bounds, we mean that we are doing this induction within some interval. So for the upward schema, the base case will be B1, and then in the induction step case, we're saying that the induction step must hold for integers between B1 and B2, and then if that holds, then we can derive that fx holds for all the integers in that interval between B1 and B2. And similarly for downward induction, except that we are starting with B2 instead of B1, so B2 will be the base case. And we just plug these induction schemes into our induction rules, and we obtain something very similar to what we've already seen before. So let's take a look at how will all this play out in the saturation-based framework after clausification. So when we clausify this schema, we obtain these 4 clauses. The first literal in the clauses, again, comes from the base case. The second literal in all the clauses is the induction step case, and then the latter 3 literals come from the conclusion of the induction axiom.
So these B's are sort of separate, unrelated variables or scalar functions too.
Yes, these are, for now, these are some symbolic values. So we have to choose what we use as the B's. And I will get around to explaining how we choose this in just a second. But first, let me do the step that we already know from induction with term algebras, and that is resolving this last part against the not LA in the premise. So we managed to get rid of that. We replaced it by C, and we also instantiated the X's in all these clauses by A. Now, to take a step back in this whole saturation-based framework, we're trying to derive Folsom. Folsom corresponds to empty clause. So essentially, we're trying to prove that some of these clauses, or like at least one of these clauses, cannot be satisfied. These literals here with the A's, they can be satisfied if the A is outside of the bounds B1, B2. So if it is either smaller than B1 or greater than B2. So to be able to derive Folsom from these clauses, we actually have to have A which is within those bounds. And this actually gives us a recipe of how to choose the B1 and B2. Because what we can do, if we want to get rid of these literals here, we can require that we already have complementary literals to them in the search space, and only then instantiate the induction. So essentially what we do is we don't only require the first premise, the main premise containing the literal model A that we're trying to refute, but we also look in our search space and check if we already have something that is bounding our term A on which we're applying induction. And if we have, then we're able to instantiate this axiom. Now, this would be the axiom that has two bounds, a lower bound and upper bound. We also have the axiom that only has either a lower bound or an upper bound. And in that case, we will be proving by induction for an infinite interval. And of course, we will only require one of the bounds in that case. So yeah, and when we have that, we can immediately, again, resolve the literals from the clauses. And we're left with something that is smaller and nicer to reason with. So for integer induction, just to summarize, we are introducing rules like these two. Actually, the first one is without the additional premises is never used because we would have to correctly guess both bounds. This isn't something that happens much. But we have a similar rule with only one bound. So either the lower bound or the upper bound. And we don't turn it on by default because this one can be very explosive and could be applied to theoretically anything and can also have many other consequences. But it is sometimes useful. If we, for example, have a property that holds really for all integers, but needs to be proved separately by two separate inductions, starting from 0 going upwards and starting from 0 going downwards, then we might want to use a rule without the additional bound to prove it by just guessing that, okay, maybe we can start with 0. Yeah, so let's see how this applies on our example from the beginning of the presentation. So we want to prove the property of the arrays if we have the invariant and if we have the negation of the loop condition. So for this, we will use the upward induction scheme and we'll instantiate it this way. So for our formula, or for the literal that is instantiating the scheme, we'll take the equality between AX and AP. The lower bound will be P, and the upper bound will be the last index in the array A. And then we apply saturation with these induction rules and resolution. And I can, again, show you how it looks like. So here I'm using this is actually a bit simplified version of it because otherwise we'll be here for a longer time and it will be, but yeah, so what we can do is now use the integer induction. And again, like in under 1 second, Vampire produces this proof. And we can see that here we have the integer induction hypothesis that's upwards on a finite interval. And yes, I'm using a different notation. So here, instead of array A, I'm using a function A, which represents the value stored at the given point. Yeah.
So actually, could you go back one slide?
This one.
So Vampire knew to apply the scheme with B2 equal to A size minus 1 because you had in your goal that J was less than A size. So that's one of the fact that I guess in your language X was less than B2 is already in the previous. So if you are asked to prove something which is ostensibly easier, like say instead of A size minus 1, would it actually be harder to prove not the full assertion, but some subset of the assertion because you wouldn't get the right B2?
In a way, yes, but at the same time, we have some theory reasoning that might derive exactly that inequality that we might need. Okay. And yeah. Okay, and so we ran some experiments with this at the time when we published this. So these are experiments on the benchmarks from the SMT-lib benchmark set, which isn't geared towards induction in any way. And these LIA and UFLIA correspond to linear integer arithmetic and possibly with uninterpreted functions. And we were actually pleasantly surprised to see that induction helped us prove quite many new problems in Vampire, and actually even some new problems compared to other solvers. And then we also ran some experiments with our own benchmark set, which was purely focused on induction. So we only ran it with solvers that support induction and integer reasoning. So the first subset of benchmarks were benchmarks exactly as the one that you've seen here, based on this principle of copying elements in an array. Then the second set was based on, or essentially the very similar to what I've shown you on one of the first slides about summing up intervals of integers. And then the third subset of benchmarks was about distributivity of multiplication over exponentiation. And again, we can solve new problems that we weren't able to solve fully automatically before. So to wrap up, because I'm running out of time, or actually ran out of time, so I'll make this short. I talked a bit about saturation-based proof search, and I think like for this audience, the important takeaway here is that it is a approach to fully automated proving that is fairly good with quantifiers and can also do some theory reasoning. And thanks to this work, our saturation-based theorem prover can now also handle induction and proving by induction, which can be useful for software analysis or math problems. And yeah, we can now prove these two properties. And then we have some further work in our group on how to guide the induction in saturation-based proof search, so reducing applications of induction so that we're more efficient. We have some work on rewriting using formulas that originate from induction, and there is some current ongoing work on generating lemmas from the induction formulas. And that's it. Thank you.